Okay, ladies and gentlemen, we'll call this afternoon's session to order. Many of us have gotten really used to CCDs, photometry and spectroscopy and astrometry, and take a whole lot of things for granted. And I asked Wayne to start thinking hard about the differences in the new camera technology and the different ways we may need to think about how we handle our data. And so I think this is partly presentation, partly discussion. Thank you.
Are we ready?
Take it away.
Okay, see if we can get the level time maybe down just a little bit more because it is a little loud in here. Plus we all hard of hearing. I'm hard of thinking, okay, as my wife will tell you. One of the things that happens in all of this stuff is I'm going to start out kind of giving you an overview of a few things that I've rounded up in the last year. As Dr. Boyd pointed out, our interesting Zoom meetings and environments, brought forth a wealth of ideas, but it also brought forth a wealth of questions. And the more I work with people, particularly something I call cloudy night wisdom, is things that I find a lot of interesting opinions about facts. I like to have opinions and facts. There we go. Just make sure I stay in range here. And so with CCD cameras, going back and thinking over things, it really dawned on me there's been a complete evolution of stuff that we've done, starting way, way back in the dim times. I have no idea what these slides are going to do, so I'm going to make it up as I go. Let's see that slide, please. Okay, so what I want to do is start out and maybe focus a little bit on FITS files, because that's something that I heard a lot of questions in here about information that we wanted to know about images that we can't find in the FITS files when we go to look for it. The other one, we'll take a break, and then I was going to talk a little bit more about something about impact of sensors, managing exposures. There's some interesting exposure strategies. And then what I want to do is kind of get a little bit of discussion going on. And the idea is that being introverts, like we all are, that probably won't take long, and we'll get out of here and be off to bed. So let's start with the next slide, please. Okay, so one of the things that's really impressed upon me in some of the things that I've been working with, a lot of people I talk to, a lot of amateurs, and I mean the pretty picture crowd. What we're finding in the pretty picture market is people are getting bored with pretty pictures. So Arnie, I think that certificate for the 1 million exposure of M51, it should be in prep. I think we're finally getting to that level. Okay. Matter of fact, I think we did a paper on a star in that at one point, so I contributed my part. But the thing is that there's a lot of things in there that we take for granted. We read, we understand some of the things about the vocabulary, but we just don't understand how it really comes together to inform the images that we take. And there's things like background contaminants. There's things like just water flux ratios. There's things about transforming your filter data so that I can take data in my backyard and then you can use it in your backyard, and it'll be an apple-to-apple comparison, particularly if we're doing something like a community collaborative type environment. The other thing that we get into is something that's mentioned here a couple of times. The bright sky is definitely ours, and there's more and more things to be seen in the bright sky. A lot of new ideas that are coming out of cell evolution and stellar work are not available to the professionals now because their telescopes have gotten so over-allocated, and also they're going to larger and larger apertures. One of the things that's happening in the world right now is consortiums are taking over telescopes, and the time allocation committees are actually starting to exclude more people. Second thing that's happening, how many people in here have a half meter? Quite a few. How many people have access to larger telescopes? Quite a few. The students here are using Las Cumbres, the 0.4 meter. They have, I believe, a 1 meter and a couple of 2 meters that you can use. It's all about getting data, understanding what that data is telling you. It's like a little crying baby. You know it's crying, but you don't know what's in it. And you have to take your time and noodle that information back out of it. High cadence is something that we don't really see in the professional world too much. We've seen it here at SAS for a number of years. Gary Vanderhagen and Bruce Howard have both been working with high-speed photoelectric spectrometers. How many people started in PEP? What did our name used to be? Okay, SAS used to be IAPPP West, and that goes way back into the dim time. Jerry Foots brought a list of some of the really, really old guys. We'll have to talk about that here at some point. But we're also seeing new instruments come online, particularly in spectroscopy. We're seeing a good representation from the commercial market in a number of areas. We're seeing the thirst for higher and higher resolution. That's called aperture fever in our world of spectroscopy. The more resolution you need, because guess what? It drives aperture. You need more aperture, more light gathering capability. Long focal length, not so much, concentrated a little bit. We're also seeing that we need to design our own instruments to meet our particular observing needs. I'm not going to get into spectroscopy very much at all, except to talk a little bit about some of the impacts of signal to noise ratio in that area. And the other thing that's really coming on that I see is informatics. There have been a number of targets that were chosen here over this last year in which there were things like spectroscopic binaries that were being treated as a single star. There were things like background contaminants. If you play in the test world, you're chock-a-block full of background contaminants. Gaia can help inform a lot of that. Gaia Confusion can even help inform that. It won't tell you what's there, but it'll give you a heads up. Maybe I want to ask somebody for a big expanded image of it. Maybe I want to do a minute or two of speckle on it, just to see what I'm really dealing with. Am I chasing a ghost in my data, like a pesky little background contaminant that's going frisky on me? And there's 25,000 databases that are available at your fingertips through coordinated software, which we'll get to here in a moment. So next slide, please. So there's been a couple things going on. Starting back in about 1969, in October, is when in the lab at Bell Labs, they were trying to get memory to work, and every time they turned the light on, it forgot. And my friend John Bowie was in the lab when that happened. And he said, wouldn't that make a good imager? There was a good choir in there. And I think it was in 1969, October 19th, that they published the note that essentially established what the CCD could be. And about 18 months later, they had a little frozen can of these things that they were taking around to the major observatories to say, try this out, try that out. Hans Zinnecker was using one of the early ones. Actually, he wasn't. He was looking over the shoulder of some guys that were using it, and they were having trouble with their scheduling. He said, okay, Hans, you get 20 minutes. What do you want to do? So he slews over to this object, and he takes an image, and there's a star, and because he had good high dynamic range in a short period of time, he saw an object on one side and an object on the other. And so it became 2, 1, 2. That's a famous jet knot stream, because then they said, oh, geez, Hans, we're still having trouble here. You get another 20 minutes. So he moved up and he found another series of knots. So if you look up the Herbig-Haro object, HH212, you'll find a long string of them. The thing was basically discovered serendipitously by using this newfangled CCD technology. And of course, that blew the lid off of it. What we saw, though, was that when people were making CCDs back in the day, there was only like one of them. They behaved roughly the same way. They started out fairly primitive, and they evolved up into an area. Some of the really old cameras at Kitt Peak, for example, have some circuitry up in there that's called the bias circuit. We call our frames bias frames. And there were various ways to read those chips out that you could just get the Johnson noise off of that bias frame, independent of what the image array was doing. If you took the image array all in one go with the so-called 0-second exposure, the vocabulary said that was a 0 exposure. So the Kitt Peak vocabulary, has got some stuff in it. I heard IRAF mentioned earlier today, some of the aspects of IRAF. That thing's been around for a long time. I plan to touch on it a little bit later in the symposium, but I will cover a little bit of it here. So if you think about it, the CCDs, and what I've been talking about leading up to this was old thing. And that is the CCD, each image pixel was made to be statistically the same in behavior and in response to all of its neighbors. It was a very simplistic little device. The old bucket brigade would take information down. There was a thing called charge transfer efficiency. And you could just draw a vertical line on a column and you could see how well that worked. How noisy it might be, as well as what was the efficiencies. 6 nines was a good number, 99.999%. So the pixel value at the top should be about that at the bottom. You can do it with zeros, darks, you can do it with basic exposures if you play a few games. Most of that was being driven by scientific needs, but quickly they began to make a wealth of CCDs. The medical imaging market picked it up. About 80% of the CCDs that you guys have, your SBIGs, your Apogees, cameras along those lines, came from the medical industry. They were adapted and converted and put in special situations that we could use them as photon counting devices. Okay? And so that kept going to newer things. We got smaller geometry. We started adding multiple channels so that when you did a readout, you could see 4 quadrants on your image had different colors. We began to go even smaller. And then all of a sudden, we switched from using a MOS type technology to using something called a complementary MOS technology. MOS is pretty much current driven. CMOS is pretty much voltage driven. And there's a whole different paradigm shift that's kind of going on in there that's going on. Now we're getting into this newfangled stuff called scientific CMOS, because we've gone around through industrial controls where they're looking at cans whizzing down a market line, where they're looking at low light imagery to see the bad guys stalking around behind the blister pack lights that we all know and love, and just high dynamic range situations. They're coming back now in medical imaging. Stan, I think you do a little bit of that. Where you're starting to use fluorescent dyes. So what we're looking for, and you'll see this in the Andor chips, for example, they're real peaky in the green. And these are called electron multiplying CCDs, EMCCDs. Well, they're that way because they're trying to drag out that morphology. If they can get a little hint of cancer for you, then they stand a chance of saying, well, gee, maybe we need to dig into this a little bit more, or you get your clean bill of health and you move on. We want to cover pretty much what the atmospheric window in optical wants to let us do. I call it from 3,300, that's a good day, at a high altitude, all the way out to somewhere around 67 to maybe 7,000. The reason it really cuts off at 7,000 is because we have all these atmospheric tellurics. We have techniques that we can back those tellurics back out. So your science can still extend up. But you notice that the chips kind of roll up and roll down in a certain pattern. Take a picture of people. That's roughly the curve that matches what people look like in daylight. Once again, we're trying to use cameras and sensors that were designed for a multitude of markets to meet very specific needs. And as Arnie is quick to point out, I happen to agree with him, you can work with just about anything. So here's the part that I have to get to. Based on Arnie's advice, don't spare the natives. Okay? For those of you who know me pretty well, I dig the bedrock on stuff. I want to know what that 1 or 2 photon anomaly is, and I get over-focused on it, and I'll make it sound like Apophis is getting ready to hit tomorrow. But it's not to worry, says the Arnie as he dances among the data. We do work around these things. But the one piece that was critical to driving this particular session, which has really got me on the spot, and thank you for letting me pace around, is the idea of this thing called, telegraph noise. Thank you. Telegraph noise is something that's been popping up all over the place. And I haven't really seen a good explanation of it or pattern. And I dug into the literature, and the more I dug, the deeper I got, the more complicated it sort of became. But it was also understandable and knowable, but it was also kind of frightening in the way that we did things with old think and the procedures that we took where we made these master single slides, or we had a single gain number that we worked that applied to the entire CCD array. That's why I'm saying we need to think about doing things a little bit differently in our approaches. Now, there are things like PIN diodes that I mentioned earlier. You can chill them, you can do interesting things with them. They have interesting spectral responses. Again, it was like Gary Vanderhagen and Bruce Howard are actually counting photons. You can see on an oscilloscope when the photon goes by. In the cosmic origin spectrograph, hard UV photons come along so infrequently they use a baby book to name them. Okay, Poisson actually works there. When you get photon counts up around 33, it turns into Gaussian. Guess what? The whole world loves a Gaussian. FFT is a Gaussian process. All kinds of math that we do, we impose the Gaussian on that, and then our math becomes just so much easier to work with. But we'll leave the PIN diodes for another day. So next slide, please. Okay. One of the things that we have to remember, and I saw a loop on this with Steve Shore, Dr. Steve Shore, over the last year. And he was talking about a CD, and I asked him, was there any way that you were seeing any of the residual in the local stellar medium? He blew it off and kept on going, because that's not what he's interested in. Later, 6 months later, he turns around and he says, we actually looked for that and we found it. And it helps to inform things, as we can get a light curve that originates, and we see it spectrographically. As it begins to propagate in different ways, we see it delayed more and more and more in terms of the path length that comes back to us. And we can see things. We can see things like gross, low-resolution energy curves coming back out of those light echoes. Now, the light echo assumes that you've got some medium to shine it off of. Most of the time, you don't. But when you do, you can get at that. And you see spectral signatures in that, which is something, as an ISM guy, I found pretty interesting. So the signal starts way out at the source, kind of like this, this projection screen. Got some red and some blue. Okay. So as it moves through, there's things in the middle, cloudy stuff, with really, really, really high densities on the order of 10 particles per cubic centimeter. Anybody here work in high vacuum? Anybody ever get close to that in high vacuum? No. Do we like to? Yes. But that's one of the reasons that astrophysics is so important, because those are laboratory conditions that are perfect laboratory conditions that we can work with. We can't make here on Earth. We can't make a parsec scale cauldron that we can look for how grains develop other molecules like polycyclic aromatic hydrocarbons and all kinds of other goodies. Those are things that are out there. Those are things that drove astronomy from the very beginning all the way till today, and it's going to be happening into the future. Once that light gets down to the Earth's atmosphere, it begins to hit various things. Or it picks up some extra signal, for example, aurora. We have lived in a peaceful time. The warning right now is it's going to start to get frisky. The sun's waking up. We're going to begin to see green light at night. It's going to be blended in with our images. We're going to begin to see some red light at night, particularly fringing in some of these things, particularly with these smaller scale CCDs. And we're using back illuminated CCDs. Bad news, back illuminated CCDs used to fringe pretty badly. Good news, we've gotten a lot better at making them smoother, okay? It's because of technology advancements. The sensor itself, well, actually, let's keep going. So then we hit the telescope. So the telescope's got all kinds of stuff going on with it. It's got dust on some kind of a coating on your mirror. The coatings are going to have slight changes. Again, the stuff that I like, things you guys don't have to worry about. Comes up through a couple of reflections and starts getting into the camera itself. As it goes through the filter, you've got dust donuts, those evil little creatures that haunt us all, particularly for those of us who work out in dry, deserty type environments. And then we get through the windows and we get onto the sensor itself. So if you think about it, the source out here is doing exactly what it's going to do. And each one of us is going to have a variable and different opinion of what's happening inside of our telescope. And if we want to talk with each other about our data, it's incumbent upon us to characterize our system by using well-known sources all the way down through the data analysis packages that we use. We've seen things where they rectify data. And who was it earlier that asked about flux conserving? Okay. Are our algorithms flux conserving when we do these de-distortion algorithms? And that's a critical thing. That's one of the things that bugs me, because I work with ISM DIM stuff. One of the things that we see with these new sensors is because they've gone to a back illuminated situation, quantum efficiencies are coming up. Quantum efficiencies are worth what? Quarter of a magnitude, maybe? Half a magnitude? Not a lot when you think about it. But guess what? It's a little bonus in our pocket to help us beat down the noise that's coming along and come up with these sensors. Okay? So we've been doing things with zero images. We've been doing things with dark images. And that was something that we woke up rather rudely about 4 years ago in an astrophysics lab. Because the students came back and they said they couldn't make our rubrics work. The reason the rubrics weren't working because the chip wasn't behaving like they used to. We had to update the rubric. Next slide, please. I'll blow through this pretty quickly. Early days, Herschel looked at a star. There's something variable and wiggly in there, and there were two stars kind of constant to the side. And what he did is he said, well, this one's dimmer, this one's brighter. I'll call that a 1 to 10 relationship, and I'll report this wiggly tube guy in terms of some imagined ratio between those two. Going back, that was accurate, really accurate way of doing things. Today, we rely on a lot of experience, however, observers are using subjective techniques. So the visual observing program is valid to a good degree, and I'll give you a good reason here in a moment. Around the 1800s, anybody remember what the periodic table looked like around 1850? I mean, it didn't even look like what we're doing today, right? There were things and chunks and stuff. Helium drove us nuts trying to find this stuff, right? I thought it was only in the sun, hence its name. But selenium was shown to have an interesting photoelectric effect in the 1800s. Now remember, Einstein got his PhD for the photoelectric effect in 1905. And that was basically one quanta of energy, they didn't even call them photons back then, liberating one electron to move. I imagine he had someone do the experiment for him, but the result was that was a game changer, and that's where we can really say started our ability as CCD people to quantitatively observe our data rather than subjectively observe our data. Well, cadmium, other exotic materials come along. So remember, in the 1900s, chemistry kind of got its act together, and so did that frightening stuff, quantum mechanics. As we get down a little bit later, we get into photographic plates. I believe, was it at Harvard, that they did one of the first time, I know it was the first time someone tied a camera, a spectrograph, and a telescope together, and they made an objective observation. And in other words, I could print this out, I could give it to 3 people and get 5 opinions, okay? They made an objective observation. That was Draper and Company, right? There was another fellow, an amateur by the name of Roberts. And what he did is he took a photographic plate of Andromeda that showed it was more like stars than nebulae. Remember, on January 1st, 1925, it was, who was it? Hubble and the other guy. The Dean of American Astronomy. That guy. It'll come to me. It rambles up slowly. The age is kind of leaking in here. He wrote a letter to Hubble and conceded the fact that these nebulae-looking things. Who was it? Yes. What was it? Shapley. Yeah, Arlo Shapley. He was the Dean of American Astronomy back then. He wrote the letter to Hubble that said these things are indeed island universes. The word galaxy hadn't even been invented yet. But yet an amateur, 40 years earlier, had basically shown us, put it right in front of us, objectively. Here is an example of something that maybe we should look at a little bit better. And of course, what did Hubble do? He went on with photographic plates to find a Cepheid variable out there. He managed to make one of the first, I've got to use this word now, standard candles. Okay? Because we're going to back up for a second and talk about something. So the standard candle to start the yardstick of measuring the universe. Now, prior to a lot of this stuff, these experienced subjective observers, they had a widget that was like this image combiner thing that had this slide that was a neutral density filter widget, and they put, guess what, a standard candle at a particular spot in their observatory, and they get the telescope and that thing lined up just right, they merged the two and they put them together until they became the same brightness. And that was a way that they would more or less push an objective number out. As long as we bought our candles from the same manufacturer and used the same equipment, we could come up with a better than subjective estimate of magnitudes. This whole length of this slide, we get into photomultiplier tubes, which is just some more advanced chemistry, and then we drop into the CCD, and right about here is 1969, and hence beginning some of the waves. So to summarize this whole process up, we've always been interested in the night sky. We saw galaxies that for the longest time we believed were actually where planets were forming. We thought that there might have been a nemesis star. That's how Levinson was in here, he began into orbit. That the nemesis star was coming along and splashing material off of a star to make the planets, which is like an impossible event. And then we get, in Shapley's famous letter, the idea of the island universe. We began to think, gee, there's more stars over there. There must be as many stars over here. Look at all of these galaxies. Look at the zillions of stars that there are. So here's a question for you guys. I'll start asking some questions. There's been a lot of emphasis with exoplanets and with the B filter, because that's basically matched up to our sun. Okay? What if we lived on a redder planet? Would R be RV? There's a lot of anthropomorphic behavior that's coming up in astronomy. How many of you guys have noticed that? Okay? And how many of you guys have noticed that a lot of what we consider to be the big questions are dealing with things like, where did we come from? That was mentioned earlier, things along those lines. How many of you guys are really aware that microwave communication was a hot topic at Bell Labs? They hired astrophysicists to come in and use radio telescopes to try, because radio astronomy is not an easy game. And what they were doing is they were letting these guys explore the universe to develop the technology that was desperately needed. And around 1990, we saw Bell lose interest in that. Their professors read like cheap. And the reason was they invented fiber optics. So we were able to move stuff underground, regardless of the weather, and do the communications. Lately, we've been seeing a de-emphasis in spending in astronomy because we don't understand what we can harvest from the heavens. We seem to be over-focused on finding some Earth-like planet. I guess maybe that's a marketing ploy for Elon Musk, so he have a place to go in his fancy rocket. With 144 people that will be chosen at random from Tesla. So if you want to be part of the people that leave the planet, go buy a Tesla. It's pure speculation on that one. Okay, humorous speculation. We're down to a point right now where with things like ALMA, I believe 2 years ago they discovered, maybe like 2 years ago, COVID's kind of warped my sense of time. They discovered sodium chloride and magnesium chloride in the ISM. Kielens in the Netherlands, they have been working with things called polycyclic aromatic hydrocarbons. How many of you have had some today? Okay, he's drinking some right now. A cup of coffee is a PAC. Caffeine is basically one of those kinds of molecules. If you look at the ISM, it's a frat house. It's got formaldehyde, it's got alcohol. Somebody once quoted amount of ethanol that was in a nebula in fifths. Okay, we also have a zoo up there. Other things that we find are there's caffeine, and other PACs. Chocolate, by the way, is a PAC. We have salt. In other words, the critical ingredients for life at a frat house and byproducts of living in a frat house has come from radio observations. It is so rich, the lines in the spectra are so rich that we're having trouble disentangling what they really mean. But we're able to find molecules that cannot be built using standard processes on Earth through that process. The optical informs the radio better informs the chemistry, and it goes full circle back into pharmaceuticals, through all the things that we know and love and use every day. Let's go to the next slide. Remember, too, It used to be the colder we made things, the better they were, up to a point. A lot of LN2 cooled cameras are still in use today. Some of them are running down not to 4,000 degrees, but to 4 Kelvin. And these are heating and cooled IR sensors that are being used in long wavelength optical. These things practically have no dark current. We just wouldn't take darks with them. Zeros were, we could take one every couple of weeks. The bias frame was kind of interesting because it would produce a number between 99 and 101. That bias value was in there because they had to boost low signals coming out of these arrays to a point that the analog to digital converting circuit didn't go nuts. It didn't misrepresent your data. So what was important to know was that guy dialed in and ready to go. That's why we asked it to give us a lot of readouts for that bias number. That thing became known as pedestal. Now remember I mentioned Claudionite wisdom here a couple of days ago, and I've heard this from some of you guys here, that you put a big number in as a pedestal, so when you do your mass or subtract, you don't get negative numbers. Okay, John's shaking his head. Brother John, you're in the choir. Amen. So these are things that I think that we need to be a little crisper in the way we talk about them. And we need to strive for better clarity in our overall community. And that's both for the pretty picture artistic guys, and I love them, because they scared the heck out of us one day, but they have really stretched out an O2 feature that we knew wasn't there, and what did we miss? So the idea is that as these people come along and they develop their skills, and you got to remember the artistic astronomer probably is practicing his photometry better than we do. They actually focus. Now, the problem comes when they go into their magic artistic software, and we go into our magic asylum-inducing softwares, like IRAP, for example. Pixel sizes started out being pretty big. There was kind of a rule, and this goes back to one of the fundamental basic assumptions that we have today to learn not to have any. We've got to lose this idea that every pixel is the same. The idea that you had a 24 micron pixel, that it matched the plate scale of your star, the apertures didn't matter, everything fit into one pixel, that pixel value was sacrosanct. As things got a little bit fuzzier, as they got like more down into the tens of thousands of dollars per sensor, we began to defocus a little bit and use more of those pixels. Who was it here today that mentioned, Richard, was it you? The KAF1001? Okay, great chip, 24 micron pixels, right? Okay, and we've seen that come out more and more. Nowadays, we're getting down into pixel sizes that are in the, what's good numbers? 12 is a good one, 9 is a good one, 6 point something, 3.74. Sorry, just kind of mumbled. And as they get smaller and smaller and smaller, what are we seeing? We're seeing noisier and noisier images, right? Ta-da! Okay, I reached about the 15-minute point here. Telegraph noise, you go lose yourself there. So what we're looking at then is we began to see well depths in the early cameras that were greater than 65,535. And we developed the concept of a number called gain. And gain was a number that allowed us to scale 100,000 down to fit comfortably in that 65,536. What did we sacrifice? A little bit of dynamic range, because we picked up some fuzz in the least significant bits, right? You want some more fuzz? Just stay here on the planet. And, you really want some good fuzz, I tell you. Go over to Dr. Boyd's house or Tony Roddo's house. That's like on the wet rock. And you'll get lots of good, moist, photon variating fuzz for these things. All right, next slide, please. We're using Peltier cooling, which can work or not. There are a couple of cameras on the market right now in areas of the Southwest that you struggle to get your camera down to 5 degrees, let alone -5. And there are people that are building jackets to go around them. We saw one demonstrated here, 4 years ago? Yeah. Some people are putting like air conditioners in to go around them. In the wintertime, I go outside, I'd have to warm my camera up to minus 20 degrees. We see dynamic shifts in the temperature from, I heard a report the other day of 50 degrees in the observatory to down around 40 degrees at night in ambient temperatures. So those are things that we have to struggle with. And so that means it's incumbent upon our requiring of our vendors to give us cameras that we can actually cool and manage the temperatures. We saw back in the day the emergence of a widget called an anti-ballooning gate, ABG. Heard that mentioned earlier today. The ABG is structure that sits around the pixel that as that well begins to overflow, it attracts those electrons and bleeds them out before it has a chance to damage your data, in theory. The more that well fills up, you get a higher and higher flow rate out of it. So you get a nonlinear part of the top of those kinds of pixels. As long as you stay in the linearity range, you're okay. What does that mean? Doubling your exposures, essentially. Take a number of lower second exposures to compensate for filling that well up. And what do we lose, brother? We lose dynamic range. So now we're beginning to see some new ideas come about. I'm going to hold off for a second here. Back illumination is where they actually took the pixel or the material like this. They built a pixel up here and they left some zones on the bottom. They flipped it upside down. They would basically skim off the back substrate. The photons would hit that back substrate, and that would liberate the electrons. The little wells would capture the electrons, but the pixel structure was down below. Otherwise, what they did is they did the same sort of thing. They carved the well like little pits in this substrate. They built the pixels on top of it. And now what you got is it's like looking through, looking through like Venetian blinds would be a good example. You know, you've got stripes in there that you can see light and stripes in there that you don't, and that's the structure. That's the electronics that you need in order to get the data out of that chip to achieve your goal. Okay, so now we're into even newer pixel layout schemes, even in terms of new processes. So next slide, please. This is my favorite. It took me a long time to figure this one out. HAD stands for Hole Accumulation Diode. And it's this little pixely thing that they stick underneath the pixel. So the little dark current's running around, and he's got like a non-photo-liberated electron. It sees that diode and goes in there, and it doesn't wind up in the register. So what you'll see is if you take a 0 and you take a dark, and you say, hey, IRF, tell me the means of these things. Those mean numbers will be the same. You get a counter to. But guess what? The variance goes up as you increase the dark exposure time. And so what you're really looking at there are manufacturing differences in the pixels. So what will I say at the very beginning? We have to disabuse ourselves of thinking pixels are all the same. They're not. We used to think of one sensor. Now we think of a mega sensor. Each of these little guys is going to have their own business to deal with. Then they added something called correlated double sampling, particularly CMOS. And what happens there, and this is something that we saw in the difference between two vendors' chips. One of them was noisier, the other one was not. So we talked to the quiet vendor and we said, what do you do? And they basically fiddled around and they stretched out the reset time. And they slightly lowered the reset speed, they slightly lowered the readout speeds. And what they were able to do then is they were able to discharge their pixels more deeply and more uniformly. Because if I walk up to something like the capacitor and I start to bleed it off, that curve comes down exponentially. If I don't give it enough time, I get some residual in there. How do you fix it? Well, you still do stuff fast. But what you do is you go take a snapshot of the pixel after you think that you've reset it. And then what you do is you come along and you let the exposure go ahead, and then you take the well value out, you subtract away what you had sampled from before, and then you report that as the ADUs for your observation. You reset it, sample again, and go. Guess what? That sample value every time is going to be different. The faster you are, the more variation you're going to see because you're surfing around higher up on that curve. So the whole accumulation diode was something that we had to learn to live with. The quiet chip did a really good job of it. You cool that baby down, and I think that's the one that Dennis Conti was doing a lot of his work with the transit exoplanets. The other thing that we began to pick up was the fact that back illumination was becoming more and more affordable. If you've been watching even the big marketing buzz, back illuminated chips, what, 5 years ago, they were still kind of spendy. Now, the QHY 600 and the T96, those are back illuminated chips that do a really good job, and they're very affordable. And thanks to things like this Canon camera, and of course, I think that's a Sony chip in it, doesn't it? It basically is that technology. Billions of guys are using stuff. We're using them. Every time we buy one of these silly little cameras, like mine's got 3, I think, well, a couple of them. The idea is that they have put so much development time into making these things inexpensive that we're benefiting from that now in the market. We used to benefit from the medical market doing things, and the security market, the industrial market. Now we're coming out from the consumer market. So the good news is they're still working in our behalf, but they keep making the pixels smaller and smaller. Another thing that we see is we see chips that have processors built onto them or into them. It's now possible to merge intellectual properties together to build these chips. Dr. Q just moved the readout and RAM into a separate area that took the current flows and so forth away from that chip, which really quieted it down. I was talking to Arnie a couple of weeks ago, and I told him, you know, I went and I took a dark and I put it in DS9, and I said, show me what it is. It was bright supernova off the back end of it. And I'm thinking, oh, no, what have I done? I just spent $4,000 on a camera I can't use. It turned out the numbers were only like 6 or 7, and it just was stretched so far. It just logarithmically really scared me. So one of the things that we don't understand a lot about is what are these things doing to us between the time that they say, stop the sample and get the data, and that they report it out the back end. Thanks to work by AADSO and others, what they've been doing is asking the vendors exactly what that is. Is it there or is it not? If you go into some of the process cameras, yeah, it's there because that's what the customer wants. In our case, it may be there, just not used, or it's just never there to begin with. We're beginning to see things like, you know, the digitization. I think that what I meant by that is, I think something volunteered a word for me right here, is the thing that we're having different amps for every column now. Because we can build them small, we can manage them, and that way we can read the chip out much faster, much higher cadences, things like that. How many gains do we have now? And some of the vendors, what they do is they assume a uniform light. Uniform is light. When was the last time we got anything uniform? Okay. So what they'll do is they'll take an image and they'll supply that image. They'll put it in a database with your chip serial number on it. And you can go get that image, and that's supposed to help balance some of that out to within a few percent. Okay. So are we doing it? Are we not? Can we do it in post-processing? Yes. Are we, you know, we've got to be careful with the vendors that we get. The other thing that we find a lot of times, and people complain about this, is the software packages are there to help us. You know, we think we can take the data in a bucket and pour it into the top, and how much data do you have? You must have a bucket. You know, a sneaker bucket. You put your sneaker bucket in the top, and LaTeX pours out, you know, in AMS format. So you're ready to just publish right off the bat. It's a goal, okay? We're being driven quite a bit by the market. That's something to always bear in our mind. Always bear in our mind. Next slide, please. So the latest thinking that's going on is we get the CMOS, the scientific CMOS, and we're getting into this whole bunch of noise mitigation schemes. So let's keep going. Covered most of this already. So at this point, let's take a quick recap. What we saw is we were being driven by pure sheer monkey inquisitiveness, anthropomorphic type of ideals. So you go around and say, who's here with us? What's going on? How do these things work? Yes, Lord, I get the message. But the idea is we began to really delve into this. We found wondrous things in the sky. We found things that stars were not constant. And they knew that. Algol. Remember back before we had TV? These Arabic guys did way back then. They'd be lying around going, gee, what do you think about the new camel market? And they noticed this, hey, wasn't that a little brighter last night? And somebody started writing this stuff down since they knew how to write. And we basically found out that the star would go through these periodic comes called the demon star Algol. We noticed other stars were doing the same sort of thing. We noticed there were various brightnesses. The Hipparchus, geez, well, back in the Greek days, gave us a scale of 6, which we still don't understand. Is it 2.511 or is it 2.50 precisely? Those kinds of things. We saw an emergence of technology, mainly because it was being driven by advances in science that turned into engineering. Remember, we scientists find stuff, engineers make stuff out of it. What happens now is those engineers started giving us selenium, photomultiplier tubes, CCDs, and now we're into CMOS. Now we're into things where we have complicated pixels that are giving us our data. And it's just up to us to do the bookkeeping on that data. All right. I probably, hopefully, generated a few questions here. Are there any questions up to this point? Tony? Don't. Never been. Never been.
Yeah, just okay, CMOS, okay? To bin or not to bin?
Okay, voting. Those for binning. Come on. This is an interactive game. Raise your hands. Those for not binning. Okay. What?
Or does depends.
Depends. Arnie's tombstone. Okay. You're right. Also, what technology? The reason I say don't bend CMOS is because every pixel is unique. John just pointed this out. We read quads of them. Okay, they read quads because that's what a bare mask looks like. And if they want to turn a color camera into mono, they have a special algorithm that can do that just by reading each quad and putting them back together again. If they really want to read out at really high speeds with the same QHY600 sensor, they do it in such a way we only end up with 10-bit data. If they read the whole quad in one go, excuse me, not the 600, in some of the lesser cameras, it comes out as 10-bit data. And then at the other one, they actually have a 16-bit ABC in there, so we can get a real number out of it. So it goes back in the mix and match department, and is qualify all your cameras. And this is one of the things we really need to start talking to each other about. Which cameras do we find that work? Which ones don't? How many use CMOSs right now, Tony, are on Queen's list?
With the different gains and the different amps and the way it reads it out, do I get true data? If I've been across the spectrum, am I losing data?
Yes. Because you're dragging information and okay, the spectrograph doesn't produce all of the data for one wavelength and one set of pixels. It has a little bit from this over on this side of the wavelength, kind of more the one in the middle and more to the one in the left. As you start binning those, you're dragging more and more information in. The question about not binning is this. Those pixels have irregular behavior. If you leave them unbinned, then you have a chance of qualifying what that noise is, of fixing that noise should you need to. If you bin it up, it's summed up inside the camera, and you lose any sight of that. Now you begin to beat it down using statistical methods. Good luck.
If you're really anal, it's also wavelength dependent. and you want to, in fact, characterize your gain for each pixel and floor level as a function of wavelength, so that as you calibrate it, you actually have access to a lot more than you could do that on top of it.
Okay, okay, hold on. I need to borrow you Bob's. Bob's, come forward, please. Okay. Just these two, and I need these particular two in random order, okay? And I have been describing this using 3 fingers. Now I got to be in the light for the moment, okay? I've been describing this using 3 fingers by saying, where is the peak of that? Believe me, you can get rudely in trouble quickly using 3 fingers. In building a Gaussian fit to a curve like that, let me get out of the light over here so the camera can see it for a minute. If you're building it in a Gaussian fit, then what you're doing is you want an odd number, because you're trying to get the ratios of the guys on either side. So if you've got 3, you're in good shape. If you've got 7, you're in even better shape. If you bend, you got 1. Keep going. Yeah.
Am I harming the stats, the noise, and the way the noise is calculated on the CMOS chip? Is that different to the way I calibrate CCD?
Okay. Fair question. And before I do that, get this guy over here, Dr. Martin.
Yeah, but what you're talking about here is sampling, right?
Yeah.
Because if your point spread function is very well defined, and you know it really well, you can get a lot more information out of those pixels than if you don't. And some of the problem is often because you do not know what the shape of your PFF is, because it's undersampled. And what you're talking about with more pixels is being able to oversample or adequately sample that PFF. But you don't have to do that. Once you have, for some applications then, once you have characterized that PSF, you can start binning up to get the improved signal rather than spreading it out over all those pixels, because you know what the PSF should be, so you don't need as much signal to get the information out.
Okay. Okay. I saw 6 or 7 caveats. I'm going to mark you down to a B- for not paying attention earlier on when I said each pixel is its own unique sensor.
Right.
Now, in CCD speak, the pixel's going to have read noise, lots of it. Okay. Over in CMOS land, not so much. Okay. So that means that you can afford to spend some of your CMOS read noise budget and still maintain really good sampling capability from a sampling point of view.
Here's the real caveat, though. Are you talking about high signal or low signal environment? Are you noise dominated or are you signal dominated? Because it matters.
Well, not only does it matter, but the noise one beats the signal. And the reason the noise one beats the signal is the real nasty noise, like those freaking little CMOS plants and those cosmic ray dudes. Okay. Okay. Okay, so Tony, to your direct answer, the word that you're stumbling around with, and believe me, I wrestle with it in my sleep at night, is called uncertainty, and it's called confidence. And if you blur that down, you increase your level of uncertainty if you're bending. Whereas if you leave it alone, and in a CMOS situation we can do that, because remember, we can get the image, and it's huge, it's massive. He's thinking, by God, I'm going to have the whole Starfleet fleet up there getting my data out of my own telescope. The thing is that you can bend it up at the source after you've had a chance to play with your data. Yes, John?
The other thing you have to remember is that CCDs are can dump multiple buckets into the readout machine. Okay?
That's right.
All right. In CMOS, no. All right. And so binning doesn't give you an inherent improvement of signal to noise as it used to do in CCDs. CMOS, all right, but the read noise is so low, in fact, in many applications, it's below the sky noise. You actually want to limit your exposures and then bin the hell out of it because you can beat down the sky noise, which you can't do in a CCD.
Okay.
Yeah.
All right.
And
So,
it's not bin it, it's stack it. I'm not using the right term.
so John, I'm going to return to that in spades here in a little bit, and thank you very much for introducing it at this point. But to sum up and get on to our next group here, we need to stand up and stretch our legs out before we get blood clots. Now, I think we're both wrestling with that up between the ears. Is pixels are not the same anymore. We can't get by with just one number when we need a million. The other thing is that in binning, what we do is we're trading off aspects of certainty, and certain aspects of that certainty were guaranteed because we could indeed make the assumption that our pixels were the same. Now we can't. So anytime that you're dragging noise from one side to the next, or you're aggregating it, and there's another devilish thing called pixel pattern that we haven't even talked about yet. But those are things that you can get into. In my work, I never bin, except when I'm ready to. I choose when I bin. I don't let the camera choose it for me. And I know where my image is, because if I'm doing spectroscopy with a 600M, I've got a whole continent of data out there that I don't even care about. I have to bring the edges in to start getting where I get signal in the blue and the red, because that's the curve of my chip. And I need to come down to where the trace of my function is. If I'm looking at 3 stars, I tend to try to point in the middle so that my target star, my comp star, and my reference star are all about equal distance out in my vignetting pattern, so that when I flat up, I'm doing to all what I do to one. Okay, so let's put a pin in it for a moment, stand up, walk around a little bit. We'll hit the next slide while we're waiting. Yeah, 5. We're old. We got coffee stacked up to the rafters. Level, yeah.
Okay, it is time to reconvene for Chapter 2. Take it away, Wayne.
All right, folks.
Yo.
I think it's, oh, God, I want to hear that. There's kind of rambling around here, kind of like I do, driving down the road. I'm going to run over your question eventually, so if I do, kind of put it in the full part of the brain. If you remember back to the grand old days, particularly if you have, like we did, a KAF 1001E, we had stuck pixel columns and dead pixels and whatnots everywhere, okay? Pixel maps were simplistic things back then. You could just erid them one at a time, or you could make an IRAP, a little magic code that would say, these are the bad pixels, and do something about it. A lot of times they would average them, okay? We'll get that in a minute. We'd have stuck pixels, dark pixels. The pixel where everything would be tracking along just fine, and then it just get, you didn't get that anymore. And then everything after that was white, right? So basically everything that had been coming down was white until it got over the speed bump, and then it started reading out pixels for you. We had things like the charge transfer efficiency is something I looked at before. One of the first things I do with a new camera, or even with a camera that's at a different temperature or something, bring it up a DS9 and just draw a projection from corner to corner, just to see kind of like what's going on in my data, just to kind of give me a sense of what that camera's doing. It's fun to do with zeros, darks. If I get a data set in from somebody, that's why I like to ask people to send me their zeros, raw zeros and darks, so I can get an idea of the statistics there. We talked a bit about the bias circuitry being the precursor of the pedestal. Okay. The other thing we talked about for a while was dark current. Dark current is where root KT, just random motion, it's pink noise, breaks an electron loose in the substrate and winds up in your pixel and gets counted as actual data. We talked about readout noise, which is the sense that every time you go through the amplifier, every time you go through some of these shift registers, particularly the accumulating registers, you're picking up a few stray electrons, kind of sweeping them up as you go along. We heard a mention earlier about spectral sensitivity. Spectral sensitivity of these chips are controlled by putting materials in when they make the process film that they put down to do magic pixel stuff with. It has a selective sensitivity. We can bias it red, we can bias it blue. There's another interesting part about spectral sensitivity. If you happen to have the KAF1001E, the E part is they coated a material on there, just a molecular material over all the pixels. Whenever a bluish electron or photon would come in, it would liberate, or actually it would fluoresce. And you would get 2 pixels out that were green. But the energy was about the same. But what that allowed you to do is it allowed you to bend up the blue end of the spectrum. What was that stuff called? Luminol? Something? I think that's what they looked with blood in CSI. But Lumi something or other. It's in one of the books. The other thing that we touched on briefly was quantum efficiency. Quantum efficiency has got a lot of dynamical elements to it, and I'll get into bits and pieces of that a little bit later on. But essentially it goes into the willingness of the substrate to accept a photon and turn it into an electron. Very basically means that's Einstein's Nobel. Other parts of it is if the photon manages to make it all the way from the star, way over there, and it whizzes through the atmosphere and it goes through everything, and it lands in the flower bed next to your observatory, you have a quantum efficiency of 0. The same thing is if it goes all the way through and it hits pixel structure and never manages to create a countable electron, then you lose a part of your quantum efficiency. If you can improve the geometry, which I think was one of the words up there, yes, that's what it was. If you improve the geometry or improve the geometry, you improve the quantum efficiency. And there are various ways to do that. So next slide, please. Beep. And usually it beeps at me, beep back. So we got this thing called the fill-in factor. How many of you guys have seen fill-in factor mentioned? Okay, good, good, good. I'm probing the community here trying to see kind of what words you guys have heard. Fill-in factor basically means how much pixel circuitry is in the way of accepting that photon into an environment where it may or may not, by quantum efficiency, liberate a photon, or an electron that you will capture and count. Okay? And then you get things like front side and back side illumination. And that's where that kind of comes in. If they can build, I mentioned this earlier, the pixel structure on the bottom and leave the top fully unobstructed, then your quantum efficiency is just going to come up because there's less fill-in factor for these things to run into, less Venetian blind material up there. All right, now we get down to the meat and coconut. I'm going to introduce you to telegraph noise. We've all seen it. It's often called salt and pepper. I don't really believe it's pepper. I think pepper comes because of an inappropriate, because you subtracted some salt from earlier. Like you made yourself a nice master file and you come along and you zip something down, you had a low rider together with something lower and you get a piece of pepper. Most of the time, this stuff appears to be the result of a trapped amount of current that's being deferred into the future. And it comes up as a little bump in your signal, maybe in the next frame, and it may have an effect where it dredges up some like-minded electrons to come in your current frame. Energy can be neither created nor destroyed, but a lot of times when these charge traps capture something, they get reset, you just lose that out of the middle of your signal. So there's a kind of a pepper that you can get. We'll get that here in a bit. We talked about clocking and clocking frequencies. You've noticed that if you do so many megahertz, your read noise will be such and such. The slower you go, the better your read noise. And overall, the better your thing. If you're into high cadence, then it's important that you clock quickly. If you're really into marketing, it's important that you clock quickly. Most of the time, blow a few extra seconds and take some time downloading your data to clean up the fact that you're adding clock-induced noise into your observations. Tony. Sheer image size, okay? I've written a little Python program called Trim, And what you do is you describe in IRAPI terms what piece of your image do you wish to retain. It puts a logical to physical mapping of the pixels on there. And you wind up with a chunk of the image that actually has stuff that you need. Like I have some images, I just mentioned this earlier, the 42-inch, that has a real noisy stripe along the edge of that image. If you just mask that away because you know you don't need it, there's no science or anything there. It's not really contributing to my overall confidence in my image. It's not contributing to my overall reliance on that stripe. Hopefully that's not where they put the guard bands for the chip. Some people use this and don't. So that's why I say don't bend, but trim. Or, I should have added this, bend after the fact. You do the bending. You add the pixels together. That way you can certify each one and get on with your day. There's a port of concept coming up on that in a second. Stuck columns are very rare. It's almost like an ABC has to fail. But they do exist. Usually those chips are rejected before you see them. Imagine if you get a little bit of nastiness like static electricity or something. And pixel scale. Pixel scale, sun's still up, so I guess we have a while. Those are things that you can really start an argument over. Just how many, it goes back to the bending argument, how many little bends do I need to capture my pixel cells or capture a quote star image? And the answer is the more you have, the better off you are, up to a point, because a lot of the software, the black body software, doesn't have PSF tables big enough to handle the number of pixels that you're oversampling. And we're using small pixels these days. We're using like 3.76 micron pixels. That's like 25 pixels square to fit inside of something that gives my nominal 2 arc second scene. How many? Okay. Raise your hand. Raise your hand as I go. How many people live and think that a 3 arc second night is good? Okay. My backyard. Okay. How about 4? You got any 4s out there? A couple. Okay. Yeah. But you got to do it. That comet's right there, and it ain't going to go anywhere. That asteroid's getting ready to hit that star. It's 6 arc seconds. Happy day. Yes. Okay. Because that's he brings up a valid point that we believe. We got to death like 4 years ago. Parallactic angle. Okay, which by the way, flex spec handles. Okay, but yeah, because it goes down to the quality of your light. Are you accidentally rejecting blue or red on the side of your slit? So that can actually change your expectation and your confidence of the actual spectrum that you're getting. And then during normal times, it goes down to, what's that word again? Dynamic range? Okay, because you're really making the fuzzy edges have lower signal to noise. Whereas the central part is up there in a comfortable signal to noise. So it goes, if you start, you can go, okay, you can stay awake at night to think about this one. If you start trying to do the error bar and stuff like that, it's nuts. So basically, you want to be able to sample your Airy disk. And there's a couple of things here. This is a good question for Arnie. He offered to answer the occasional question here. If I'm sitting with a big aperture so that I've got the fluffy parts of my star in there, what happens if I set the aperture to be the full width half max and stick it in the middle of that star image and let the fluffy stuff take care of itself?
It's noisier. You're not including all of the data that's coming in from the star. You're throwing away what?
30, 38%, something like that, 32%?
Something like that.
Yeah.
And so that, in some cases that's okay, in some cases it's not. The harder problem is where do you find the centroid of the objects that you include just one full width half max? How do you circularize an aperture that's done with clear pixels?
Yeah.
Things like that. So there's a lot of, inherent problems in trying to do a one full width
okay.
measurement.
And that sums up very well in the term flux conserving, doesn't it? Okay. And in spectroscopy in spades, because they've been rectifying images and very problematic. And Next slide, please. Oh, there's some good vocabulary in here. Vocabulary that we heard young people using. Sex tractor, point spread functions, all those things that us old guys are probably good at. Okay? So if you take a look at over time, you should go back in your library every now and then and wean out of those library images things that you put in your image museum. The good, the bad, and the ugly. Okay? And that's a good thing to do, because you can go back and say, what did I do on those ugly nights when the asteroid was going to hit the star, and how do I back everything up? It'd be nice if we could work together and collect some of these types of images and build a greater SAS museum of good, bad, and ugly images, data sets. I tend to use DS9 quite a bit. I script it. It ties in with IRAF, because it's the replacement for SimTool. And it does what it does up to a point. If you're trying to make it do everything, you're kind of wasting your time with any tool in a lot of ways. You just want to jump right into Python and get your hands right down on your own algorithms to do your own work, or borrow someone else's algorithms. But you get a pretty good idea at the telescope of what's going on. Am I focused? Do I have a good spread? Is there something goofy? Is there a bird sitting on the end of my telescope? Lissa-G stars, wonder where they come from. The aliens are done. The other one is things like, gee, that's a noisy image. I wonder what's happening with my cooler. You find out you have turned the cooler on or the cooler shot, something along those lines. Anyway, it's a great tool. It's platform agnostic. It runs on Windows. It runs on Macs. It runs on the Raspberry Pi. Okay? So you can get around a lot of stuff. You can do all manner of things, and I'll just leave it at that. By the way, Rachel Freed, where's Rachel? She has a couple of beginning DS9 YouTubes out there, and there are quite a few handy. Smart Cookie Patapata. Are any of you run against that guy? He's a Spanish graduate student that goes over IRAF for spectroscopy in an excellent way, and he's funny. And so you can use it for anything. I use it for, remember I told you I'm kind of into data informatics. I can go get a catalog, just a tab separate variable, always put right ascension and declination in column 1 and 2, and then draw little circles all over things. And then there's a bunch of stuff you can do with advanced DS9. For example, at one point, I could run Sex Tractor on an image, like a DSS image, for example. Did I get good science out of it? No. But I managed my expectation about what I was getting ready to observe. So you can see the play. Next slide. Marketing. Here's a good one. You go and you look up on the website and it says, gee whiz, I get a 14-bit ADC. I'm really not. It's a 12 that's reading out a 4-pixel pattern. Okay? And then you delve into it a little bit more deeply and you get into more and more interesting things. Okay? You go look at the data. Next slide, please. No, keep going. Here we're talking about binning combines noise. And this telegraph noise is the worst stuff, because you can't put it in a master file. You can't back it out by applying a master to it today. Don't know how we're going to do that. And remember, we said we're going to have some discussions here in a little bit. That's going to be asking you guys, what do you think about some of these tricky things up the speed? We know to trim, always bin later. And I put some numbers up here. Here's the one that you guys might be interested in of all the equations I'm going to show you. And let me tell you. If you take your expected well depth with the natural log, divide it by the natural log of 2, or you can do a log 10 of this divided by log 10 of 2, then it gives you the number of pixels, or not pixels, the number of bits in a computer word that it's going to take to match and hold all of the significant digits that you're getting out. Now, back on the previous slide, you'll see a lot of numbers. A lot of those numbers are sort of rounded off a little bit. So is that really 16,500? Maybe it's 17,000, 16,800, something like that. You get the idea. Okay, keep going, keep going. There we go. Now, we're going to talk about telegraph noise. Remember I talked a minute ago about inclusions, charge traps. Okay? Charge traps form around inclusions in circuitry. It doesn't matter what the circuitry. My wife's a read-write engineer and a channel engineer at a disk drive company. She was just retired. Okay. Clark, I think he dealt with some of these issues as well. As these geometries come down in smaller and smaller ways, the inclusions are staying, they're coming down too because the processes are getting better. So some examples are, notice the color of this part of this pixel is different from that one. Notice that the shapes up in here are just a little bit different. There's the one that's got a little fat appendix. Here's one that's got a little skinny one. Probably have to cut that one out here in a couple of weeks. Okay. You'll notice that these little areas, all the places where charge flow, there are these little tiny widgets in here, these little tiny molecular, they're more like grains. They're crystal grains that will trap current. Sometimes they'll trap a lot, they'll trap a little, they may not trap. They get rid of their energy and they get rid of it in interesting ways. You can't build a master to deal with that. It's subjective. Every exposure is going to have its own little bit to look at. So one of the things we talk about in exposure is if we can, this goes back to what John was mentioning earlier. If you know that you can take a 30-second exposure and stay within your signal to noise ratios so that you can co-add a couple of additional ones, then there's no reason to do an 1800-second one-shot exposure to get your data. Go ahead and get them. That cosmic ray comes through. Arnie's friend, the Starlink satellite, comes through. You only lose 30 seconds of integration against the sky. You can just throw that guy out and keep going. Anything you can explain logically, you can throw out of your data. If you can't explain it, you got to keep it in the container bomb. This is what we were talking about when we were talking about that pixel structure. This is some of the older pixels, and we've seen them. You've actually seen the chips. If you look in there, you'll see like the pixely part over here and a solid mask part over there on the side of the chip. And what is an interline scan thing? They pick this image up and stick it over there, and then they read it out. In the meantime, this guy's reintegrated. So they're playing this game of doing this and that, reading things out after the fact. So what you've got is you've got unit area that's sitting on a nice big airy disk, right? And it's sitting there, and you're like ignoring part of it. And then seeing moves the thing over a little bit. Now you're looking at some different part. So when it comes down to it, having this process material in your way will add a noise constituent to any data that you take, if it's a spectral line or if it's an airy disk. And that's a big thing. And it was really big about 3 or 4 years ago when some of the early scientific CMOS cameras were coming out, or some of the CMOS cameras for science were coming out. They weren't necessarily using the SCMOS technology. This was a pattern that they favored. However, this is the back illuminated and stacked array that we're seeing right now in the Sony chips. Stacked means that they actually combine 2 litho processes in one go. They're stacking technologies together. This guy, they couldn't stack very well because they'd have some stuff like this, and then right next door to it, and this is taking up even more area, right? Right next door to it, they had to build some additional stuff out on the substrate. Now, I don't know where I stole this from. Yeah, I got that from Sony. Right here is an interesting thing. This is a micro lens. This is the bare mask. This is, yeah. There's another term for that too. This is the well. This is where your data is going to live. And this is all the readout circuitry for it. So it's stacked in this particular way. A lot of the chips that we get can come in 3 flavors, I guess. One is without the micro lenses, one is without the bare mask, but with the micro lenses, and one is just naked. Well, it turns out that you've still got some pattern in here. You've still got some boundaries for these walls, these well barriers that go between these 2 cells. So the micro lens helps to combat some of that. Next slide. And this is how. So here we are with a light shield over something, and you'll see that it's really pretty ugly. Here it is kind of in a side plan view where this is maybe your photo selective area, and these are your kind of guard things. You get this lens lit, and the light that comes in focuses down, it's concentrated. It takes this area, just like your refractors do, and smush it down into this area so that essentially 100% of the signal stands a 100% chance of surviving the QE process. So that's a good reason to have it. Internal reflections be damned. The other thing is this is glass. How permissive is it of UV light or of some other spectral content? Good news is not so bad because they've got some really good glass technologies these days. They can AR coat them. They can play all kinds of interesting games on this stuff. And it does go to our benefit. Next slide, please. Because what I did is there were two graphs in something, and I swiped them. This is from onsemi, which incidentally was where Kodak wound up. Kodak, with the TrueSense, was onsemi. onsemi's dropping all of that traditional stuff now. But what I did is I smashed this curve down so that this scale was roughly on the same piece of music as that scale. And you can see that we do get a good boost by having those micro lenses there. So don't be afraid of a micro lens. I asked this question 4 years ago when we were looking at the parallactic angle problem. We were seeing something interesting in spectroscopy. What part of that machinery, that pachinko machine that the photons had to flow through, were bugging us? If you go back to the slide, please. One important question is F ratio. If I have a fast lens feeding this, or cone, or do I have a reasonable, by some definition, or some values of reasonable, that's what I should say, that will survive that lens. So those are a couple of questions that you need to pay attention to. Try to qualify them. Good places to qualify them are the photometry fields. We all mostly don't care about. Okay, one more slide. There we go. So the front illuminated guys are the big ones with the mask. The back illuminated guys are the ones like over on the right-hand side, just the previous slide. And so what we get into then is aperture algorithms that emphasize subpixel distribution of energy at the edges. How do I fit the corners of round pixels into my supposed photometric aperture by a reapportionment of energies? Easily done with a matrix. What happens if that's sitting at plenty places? Good news, tiny pixels makes this smaller problem. So tiny pixels are our friend. Even if we bend, we're sort of okay. Because, well, actually we're not. Because the pixel rounding algorithm is something we apply after the fact. And this is another good reason not to bend that, I think about it. Because you can go back and do that subsampling a little bit better. If you're doing it on the fly as part of an observing pipeline, image pours off of the camera, bang, you trim it, do it, fix it, maybe even aperture it, put some of the aperture information in a second extension of your bits file, like a MEF. Then you dump your MEF off home. That's it. Okay? All right, next slide, please. So this goes down to Bob's original question to me in a lot of ways. What is it that as a community, what are the things that we can do to improve the game? To have as a shared goal of doing a lot better with the photometry that we're doing. And a lot of it is talk to each other, like David pointed out earlier. Okay? So to determine the goal of the observation, what am I doing? And this goes to John's question. Am I doing photometry, spectroscopy, high cadence, low cadence, exoplanets, millimags versus, geez, it's better put some SPF on for that nova that's going on right now. Now we get into some interesting questions. These are questions that I've got my tricks, and I'll talk to somebody and they got a different trick. Is to determine what do we do to, what does signal to noise ratio really mean? There are a long list of different equations you can use. Pick one, pick any, pick three, maybe, and average them. There, you can bend them. Another good reason not to bend, honey. But the thing is that in spectroscopy, as we were informed by Dr. Shore 8 weeks ago, he says, man, if you guys give me 20 to 25% SNR, I'm a happy camper. Okay, Arnie, you like 25% SNR? Only if you have to have it. It depends. That's right. Only if you have to have. Only if you have to get it. No, this is spectroscopy that's in a regime that's a low light level for the instrument that brings about the amount of signal information that I need to inform my statement about the science that I'm about to make. It basically says I can get away with it. Otherwise, you draw a little bar and you say, dragons be here, right? The worst paper you ever want to try to write, okay? So we get into things like, do we deal with whopping hydrogen alpha lines? Or what about those dinky little iron 4 lines? Because these guys carry a lot of information about a photosphere. Temperature, free electrons, dynamical activity that's going on in the photosphere, subsequent, all kinds of junk goes down in there, how they Doppler shift and whatnot. Okay? Goes back to resolution. For us, aperture, aperture, aperture. Okay? So at the end of the day, we have this attitude of saying, well, gee, that was good enough. Gee, I'm just doing differential photometry sample Bob. When Dr. Boyd points out here earlier that there are times if we flux calibrate, even if it's just a rough flux calibration, we wind up with a better informed statement that we're making. So now it comes to you, it's like, okay, Dr. Buckheim, I'm going to collaborate with you. It's not like this is what I can do. It's like, what do I need? Guy goes into an accounting interview. And the guy says, Phi Beta Kappa from Yale. And they say, what's 2 plus 2? The guy goes, that's 4, of course. He goes, okay, next guy. So they bring a guy in, C average from University of Iowa, right? They say, what's 2 plus 2? And the guy goes, well, my spreadsheet says it's 4. He goes, well, okay, maybe we'll bring you back. Okay? They bring the next guy in, what's 2 plus 2? Goes over, goes down the shade, leans into Dr. Buckheim and says, what do you need it to be? That's the question the pros are asking of us, that we have to ask back. What do you need? And I have to be able to give with strong confidence, backed up by published papers in reputable journals, that say, I can do this, or our community can deliver on that point. And that's something I think over the next, okay, I know how time scales get in this game. The next 5 years, let's try to do something about this, right? We're doing it. What have we seen? I was whining like crazy a couple of years ago about flux calibration. Now we're doing an okay job of it. Now all of a sudden our data is becoming believable. And you'll notice there's been a big shift in BESS to come over to start using more flux calibrated data. Even if the error bars are fairly big, they mean that we're paying attention to what we're doing. Okay? So that's kind of something we have to always be cognizant of, and that's the fact that they've got big apertures, they own graduate students, and they have very tight data. Okay, next slide. Okay, so how accurate? Here's a paper from Albanese, 2007. It makes little sense to use photometric uncertainties measured in millimagnitudes, which is a lot of the stuff that I've been talking about, places where I run, the places that scares people and shouldn't, just because I want to know what those little irregularities look like. When you actually have systematic errors that are introduced by erroneous 0 points. So if I go to AABSO and I get a magnitude, chances are that magnitude has not been filter transformed. If it is, happy day. If I transform my data and do a good job of it, then I know what the flux is to within 2 to 3%. Because it's about a 1% here, 1% there, throw in an extra percent because of the way it will end or whatever. Okay? So these are things that, in terms of tightening up our game, that I'd like to see us focus on. And that is just what does that 0 point mean, and just what do our error bars really intend to impart. Okay, next slide. Yes, next slide. There we go. Okay. So stand up for a minute. Let's not take a break, but just stand up for a minute and move around. Talk among yourselves for a quick second. Have I managed to drive over anybody's questions yet? Okay. Oh man, I got you like my tread's full of him.
Can you go back to the slide that showed the 2 quantum efficiency curves?
Okay.
Which one is which?
Micro lens, no micro lens.
Top one is with a micro lens.
Yes.
Like I said, reduces the efficiency, and you lose a little in the blue because.
Well,
of the
actually, you
glass.
know, it's because I squished it. That's a log squish, probably, if you get right down to it. Geometric. Yeah, I kind of like trash compacted that thing down to get it roughly on the same scale.
Okay, who else?
Okay, they're scary.
So, I don't know whether you're aware or not, but, you know, when you talk about these 3.76 micron pixels, they're actually 4 pixels. Okay?
Mhm.
And you look at the gain curves that they give you, they have a discontinuity.
Mhm.
Because what they do when you're doing the 14 or the 16 bit, look at it, is they expose either 2 and 2, they'll do 2 long exposures and then 2 short exposures, and they'll take the long exposures and they'll scale the other ones with the higher 2 bits, and then they put it together. Okay?
Yeah.
So if you're looking for, you want to actually use the quote lower dynamic range because you have much less uncertainty. You've got no visibility into how well they're trying to work this onto those the 12 ones
Yeah.
that you can really believe.
That's like SDL and LDL or something like that. Yeah, and it has to do with readout speed, too. They only use 2 of them if they're reading out at 10 bits. And that's because as your bottles are going whizzing down the manufacturing line, they got to do that.
No, they actually read out all 4. It's just whether they use differential exposure.
Okay.
In the bot.
That's true, too. I mean, that's one of the modes. Yeah.
No, they do.
No, one quad gets exposure, and then they either expose so that they sum 2 of them, or they sum 4 of them.
No, it's not done with summing. It's actually done with multiplexing, the integrations.
Okay, yeah, that's about what I was saying. Summing is in the electronic capacitor sense, not
Yeah.
digital sense.
So, but you have to understand, that's why you have this, the big discontinuity. They have the sort of the,
It goes
the
on.
standard, nice, linear, full well,
Yeah.
you know, and then bam, and then they see the reading is we're fitting together in funny ways. Stuff.
Exactly.
Yeah, look at those gain transfer curves and decide what you really need. If you need low noise, okay, and you're not going to use, you're not going to use all the bits, and you've got high cadence, okay, take your lumps and use that. But if you want maximum dynamic, you got to do a little repetition because they're synthesizing 2 of those bits. And the process that does that is opaque, even when you do your technical.
Yeah. Yeah. Oh, well, let's see. Well, I'll amplify a pack about that when you get back. Or when they get back, you're here.
Another game I see played is there's the ADC, which can be 12, 14, or 16 bits. And then there's how good is the camera? So you can have a camera that has a 16-bit A to D, but the camera full well divided by the noise is only 12 bits.
That's right.
So you got to kind of watch that.
Yeah, yeah. Those are, it's all marketing mumble. And, to be fair, Sony is trying to build a really good chip. And the chip that the 600 and the other one, what is it, the 296, the shorter, smaller one. Yeah. All the same pixel technology with a little bit of changes just to make it smaller so you can have like a half-frame camera versus a big one. Those seem to be the good chips, really quiet. And I just really started paying attention. I just deciphered some of what you just said about a month ago. And then I finally got around to taking some images the other night at my mother-in-law's house. But I began stacking it through this process that I use to build data cubes. I'll cover all that here with this.
I had a question about the discontinuity that you were talking about. Are you saying that we should, depends on what we're looking for, we should either operate on the high end or the low end, so we stay away from the discontinuity?
It is discrete. When you're setting that gain, you are setting the amplifier gain. But when you get to the discontinuity point, then they're changing the way they bin things together to generate those different numbers. And so I frankly lack confidence, okay? In what they're doing is they're giving you an extra 2 bits of dynamic gain, or 2 more bits of information. They think they're giving you a number with 14 bits. I'm not sure that 2 of those are worth it. Or worse than that, if they do the ratio that you're getting linearity. That'd be an interesting experiment that I haven't done, is to check the linearity. Someone might have done that.
There was a thing about low light contrast as well.
The question I had though is that, we're aware of that discontinuity. If we plan our session, we always work on the lower.
Well, discontinuity is over a handful of values, like 2 or 3.
It's over 1.
Arnie?
Yeah, it is. If you look at it, the gain is a very constant value all the way up. And so I don't believe what John is saying.
I believe what John is
If
saying.
you can send me the reference, that is fine. It looks to me more like they're switching amplifiers rather than changing something to gain So
John,
I think
run back a slide or 2 kind of slowly until I speak. One more.
So
Go
I
forward
just don't
one.
trust what you're saying.
Up one more.
Um,
Oh, well,
the
don't worry,
difference
we'll
is
get to it.
between
I think it's coming up.
12 versus 14 bits, which is only on the
Oh, yeah.
294, which is a very unusual camera, and the QHY 600 or the QHY 286, which use the Sony chips that have 216-bit technology. So they're very different. The 294 I can believe because it was originally set up with the quad array, but all the others are pure mono as far as I can.
As far as I can tell, the 600 switches 1 pixel onto its bus to go to its ADC. And in the other case, but I think what they can do, they can synthesize the other one.
I don't understand.
If you're running something really high speed, you don't really care about the dynamic range of the image. I only see it's like is there a glass shard in it or something. You're doing some kind of like a neural net processing of the image. You don't really care about the actual photon statistics, but you got to be there. You got to have reasonable enough photon statistics to see that contrast. And they can synthesize that with a camera that you've got going on, and using like an FPGA or something like that that's on board. I don't know that they do that, but they can do that. And they do, okay, so I'm not talking about 600 here, I'm talking about cameras similar to 600 that we don't know about.
The other thing to note is if you look at the QHY site and look at the descriptions that they have for both the 600 and the 286, they just have a ton of graphs in there in which it shows you as a function of the gain setting what the dynamic range is, what the readout noise is, what the full well depth of the sensor is. And there's just a ton of information in there that helps you in deciding where you want to operate your chip for your particular project. And I think that's your best reference. And you'll notice that when it switches over to the other amplifier, which is the way that I look at it, that the dynamic range of the chip jumps up, because it's switched to a lower noise amplifier. And therefore, even though you have fewer electrons that fill the full well, you are using lower read noise, and so therefore the dynamic range jumps back up. And so these are clues as to how they're running the sensor.
Okay, I'm going to disagree with you on this one point. I think you'll agree with me when I'm done. Okay, if we can't, okay,
Here
yeah.
we go.
Mine, well, Arnie, mine's not bigger. But in the sense of things, it doesn't inform what you're supposed to do at the telescope. It informs what you want to do on your lab bench. And now you fiddle those numbers around, you look at the statistics, you see exactly what this thing's going to do against a common light source. That way, when you go take your science, you understand completely what we're dealing with. And I know you do that, because you set up your cameras to test them in all these different modes.
Yeah, well, it's true that you set up, you characterize so that you can understand your camera, and then you use that information to set up the camera on your particular
for your science.
for your science. So, you know, for spectroscopy, you may want to use the low noise amplifier. To get more full well, you may want to use the other amplifier so that you get more electrons per well. So it just depends on what your science is and how you use it.
Okay, so one place that we see that is if we have a high dynamic range signal. And in spectroscopy, we often do, except it's the hydrogen alpha that is just nuts and everything else is in the weeds. If it's in the weeds, you want to have the amp setting that minimizes the noise with that particular dynamic range.
Absolutely. So you go with the lowest read noise amplifier.
Now, the more you build that well up, the more you build that well up, the greater the chances you're going to get telegraph. That's what's driving me nuts right now.
So
I don't have an answer
that,
for you.
So you're saying that if you use it at gain 0, that you will have more telegraph noise than if you use it at gain 100 or wherever it is that it switches over.
Well, I'm saying that if you use it in such a way that you'll fill the well all the way up, but you're not, you're using, say, gain of 4, which means that I'm squeezing the numbers down a little bit. But I'm expecting that, let's have a 60,000 well, and I'm only expecting my high counts to be around 20, then I want to do it in such a way that I get the finest resolution across that 20,000 as I can. If I fill it up to 60, 74, the extended range, the 84K, that's, I think, what John was alluding to on the 600. That's where they're almost doing like an electron multiplication for you up there. They're trying to increase the contrast, because that's what the medical guys want.
So that could be my testing of the sensor said that the read noise is way high when you do the 80,000 full well sensor readout mode.
Yep.
And so I just ignored it. It's not worth it. It's like 7.5 electrons instead of the 3 electrons. So you're not gaining anything by using that particular readout.
Well, I consistently measured 4 the other night, and my camera would only cool down to around 11. I got something going on with I think it's the defroster thing on the beginning is running really hot. I mean, it's like warm to the touch. And that's got to be keeping my camera warm. But it was there about 4. That's a good expected value, given that chip at that temperature. But it had a variation in there. I mean, it's like all over the place. In fact, I think the graph is in here.
The other thing to remember is that, yeah, you have telegraph noise in there. But if you look at the read noise of the sensor, which includes all the telegraph noise, it's still around 3 electrons.
Actually, it doesn't include a telegraph. Because a telegraph noise is an independent event, image to image. And sometimes it's high, and sometimes it's low. And you've seen the graphs, and I sent you the code to do it yourself, to go to your feed and look at it. You know, if you just look at one pixel through a series across a stack, it's like this. And sometimes that's telegraph noise, and sometimes it's behaving.
And I beg to differ.
Okay.
In that the traditional way of calculating read noise is to take 2 flaps, 2 bias images.
Yep.
So you're only looking at 2 images, and the telegraph noise is inherent in both of those images. And yet when you subtract them, yes.
No.
Good.
And the reason that it's not, and as a matter of fact, I think that's in here too, besides over they got a 84-page PDF to go with this. It's like a mind-numbing strangeness. But the thing is, you go and you sample 2 images. You've got a truth table, kind of like that thing in the front of my Boston fan. Okay, you got either both of them did not have telegraph noise, both of them did, or one did and one didn't. But the thing is that any random 2 that you put together and do that technique, it gives you a good estimator. It gives me a way that I can tell you as a vendor, this is what you would expect from your chip. However, I'm stuck out here at the telescope taking 11 images. How many of those guys had telegraph noise? And those individual contributions, good news is they're relatively low some of the time. The bad acting pixels, and we've seen those guys, where they just go hugely strange, those are the ones you probably want to mask. Those are one that wound up with a big fleck of dirt that blew in from Galjo or something on a windy day. And that's the point I'm getting to, is we can't think of this as one sensor. We have to think of it as a million sensors.
Yeah. So the other thing that I've never seen anybody do, and has been on my list of projects to do.
Rewind to this morning.
We did this for infrared sensors, in the sense that you deal with a lot of bad pixels and you have to play with them. Is whether or not a pixel that exhibits telegraph noise over, say, 2 images, it's on one time and off the other, whether or not that pixel continues to exhibit telegraph noise in the future, where it goes on and off. In other words, it has some sort of a trap in there that makes it different than the pixels that surround it.
You're talking image to image or power sample to power sample?
So you're talking about bad pixels.
Right.
These pixels have telegraph noise, the adjacent pixels don't have telegraph noise.
Right.
I've never seen that.
I have. I did it.
Okay.
I published it
show
4
that.
years ago.
Give me the reference.
My paper 4 years ago
At SAS.
at SAS. The one on parallactic angle that drove everybody nuts. And whether there's a graph in there that just shows a random sample of these guys. You've got the code, I sent it to you. It's called Make 2D Stats.
Yeah.
And you can flip it around inside DS9. If you go under in the data cube, you can set up the way you do your axes. Set it to 321, and you're looking across on a particular row, I believe it is. You're looking across all the observations. Put a projection on it, just move it up and down. You'll see these guys wiggling all over the place. Stack 25 of them. We can't. Okay, really quickly, everybody. Don't median combine these things. If you've got wiggly stuff in there that's random noise, okay, we'll get to that. I bet you're going to say, how do I build a master zero in dark?
So so if you can't predict it, and if it doesn't scale with time, how the difference between a bias in terms of telegraph?
There is no difference because you just don't take them. You don't use them. Okay, nothing up my sleevey, right? Okay. That's my problem, is I need something up the sleevey to answer that question properly. Yes?
I've got some bad news for you. I've tested a CCD camera, and guess what? It's got telegraph noise.
Everything has telegraph noise. But
So it's not just CMOS. It's been there all along, but the read noise has been so high on CCDs that we typically didn't detect it. So
That's not completely true. Gary, what's your pixel size? 10, 15, 14? The one you were just referring to. The one you were just referring to.
I remember CCD camera that was.
Oh, CCD, okay.
Yeah, well, I said CCD, the one CCD camera I tried did have it, and I've tested about 6 or 8 CMOS,
Yeah.
and so far I haven't found one that doesn't have it. Some in various degrees, and some mitigate it for with various techniques. But I think it's been there all along. We just haven't seen it.
You ever heard of a Viterbi detector?
Yeah.
Okay, that was there to correct telegraph noise in disk industry. I mean,
Okay.
anything that's got an electronic circuit that has those kinds of current flows that we're sampling, and depending upon the answer, you're going to see that kind of noise. Hence, it's called telegraph noise. It's the kind of stuff that you would, like a lightning strike or something nearby. It's pure random. No. Okay, John, can you back up to the one that showed this, the SEM micrograph? That one, okay.
Can I ask a question?
David, your answer is, well, I pointed this out a little bit earlier. Notice this little defect right here. I'm trying to get that one right there. Okay. And now look at its mate over here. See how that's different? Okay. Look at this guy. Okay, there we go. See this blop right here? Compared to that blop right there. They're just different. And so yeah, one of them probably has a little higher probability of giving you a wider bell curve of telegraph noises out of it. Because these things aren't on or off, which is another little PIPA. But the thing there goes down to, we got to find a way, if we take a number of exposures and stack them up, and we see these guys jumping up away from where the nominal signal is, can we sigma clip it and better mitigate that noise? And if we do mitigate it, how do we talk about it? What kind of error bars do we use? Let's get over here. Okay.
Yeah, so for fear that we get too close to a Cloudy Nights forum at this point,
Thank you.
can I ask to try to also bring a little perspective? Is this a true statement? That these latest CMOS cameras are horrible, and they're way better than everything we've been using in the past.
Just like democracy. Just like, thank you, Mr. Churchill.
Thank you, thank you.
Thank you. Arnie thanks you for unscaring the natives. Tony.
Tony wants to another punch.
So who's going to tell the software processing guys that we don't use docs? Or, a lot of the post-processing spectroscopy, Demetra, ISIS, everybody else wants a doc.
I know. That's their problem.
You just make a synthetic.
Okay, there is another answer to this, and I think Arnie pointed this out somewhere in his literature. Make a surface map of it. What do you just did? You just sigma clipped it. You smoothed over it. I made the statement one time, you can use a number. Just take the average mean and subtract that out. You're going to leave the telegraph noise behind as salt, but you're not going to make it like muy caliente from the pepper. That means very spicy. I forget, I'm from Colorado. We actually speak in those terms and run around with our lips on the carpet. Huh? Muy bien. Mañana.
I just remembered which CCD camera it was that I measured the telegraph noise on. It was a Princeton Instruments with a back illuminated E2V chip, 512 by 512. The camera sells today, if you can get one, for 65 grand. It sold for 20,000 when it was new. It was a very, very good professional camera, and I was shocked to see telegraph noise in that.
Well, I got some a bunch of zeros off of an E2V Jensen. It's a couple years old. That showed it was a little bit of waviness in there, but it wasn't nearly as bad as what we see with these tiny small pixels. The smaller the pixel, I think, the more you see the true effects of this telegraph noise. And I have a funny feeling to do with the fact that, can you go like one slide down? One more, one with an image on it. Oh well, it's in there somewhere. We'll get to it. I think it's coming up again. Yeah, right there. Wait, that one goes good. Okay. So up here, you see these little transistors and things in there? This is a FET-like transistor. And essentially what it does is it takes voltage over here and mirrors it down through this situation here. And in such a way that it does a non-destructive read of the pixel while allowing it to go out and be, essentially, you drop a load, which is that amplifier on that pixel. You've got a copy of the voltage. You don't have the voltage itself. Then when you hit the reset, you get that decline, and at some point down there, it stops, so you've got some residual, and that's where that correlated difference sampling comes in. Because they just take a picture of that, and then they compare it later on for something else. I don't think we should have. No, not in this particular little cartoon. Okay. All right, all back together. Shall we proceed? Next section, please. All right. A lot of questions I got. I talked to a bunch of people before I came here. Half of them didn't show up. But a couple of really interesting questions came up, and that deals with like things like just going with old think versus new think. Okay. One of the things is memory. Okay, 16, 32, 64-bit. We got this sense of Indian, E-N-D-I-A-N, which started some war in Gulliver's Travel about which end of the egg did they open first. Sounds like Cloudy Nightfall. And then what we get into is, what operating system do I want? Is the processor like a little Indian? Unix would come out Xenu in the memory because you swap them and then swap them again. So that's kind of a little statement that you see sniffing around. you get into things like the Intel versus AMD. Okay, holy wartime. How many people like AMD? How many people like Intel? Okay, I like Intel because of the math kernel system and because they got special instructions that just run like a hot bath. Okay, AMD not so much, and they trade off. So next month the statement, or next 6 months the statement may be different. We're seeing this new kid on the block called an ARM, which is slowly being superseded by a couple other guys. And the last one I was around in the drive industry was RISC, the RISC-V. And it's just a package. It's just a set of intellectual property that you can drop into a mask build and build it inside of your chip. How many people here use Raspberry Pis? Bob's using one. Yay! Okay, got Linux on it. So what happens then is that has an ARM processor in it, but if you look at the little chunk and square thing that you get on there, there's a lot of junk in there. How many people use Arduinos? FlexSpec. Yay! FS1. Okay, that has a single chip that's got a bunch of things in it. It's got an IMU. Actually, I don't think it has an IMU built in. It does have like the serial ports and a bunch of the parallel ports and all kinds of junk in there. There's like all kinds of gruff up in there. All right. The other thing we hear a lot about, and Greg Jones, Greg, yeah, maybe I didn't see that. GPUs are something that are really interesting. If you can take a problem like a pixel, and this may be something that I should get Arnie and Greg Jones talking about. If your pixel will fit inside of the memory architecture of an imaging thing in a GPU, you can do the whole thing shebang, 30 milliseconds. Dr. Steve Hartung applied that process to Pan-STARS frames. And he cut like a minute per frame to like milliseconds per frame, and he went 2 orders of magnitude deeper on the noise model. And that was his thesis. With images from our AAF 101. Okay, next slide. Don't be thinking bullets. The first word of FITS is flexible. My gosh, it must be more limber than a yoga instructor. We've got every kind of keyword that didn't exist imaginable inside of FITS files these days. There are 4-letter extensions. I like them that way. DOS now, not DOS, what is it? I'm talking about Windows. Yeah, I think DOS was stuck on 3 characters. Windows was for a while. You can use lots of them now. Please, people, everybody, software vendors out there, don't put spaces in file names. It just honks everything up. Fixed names is the first thing I do in a script. Make sure everything is set. You can have headers, and yes, you can have more than one chunk in one FITS file. And we often see that. If you ask a question one time, how do I get these tabular data out? We'll wave the chicken at it and something will happen. The reason is flexible. Everything's flexible. There are modules that different observatories and whatnot wrote. Remember, back in the day, there were all these observatories that were taking data, and I don't know where this came from. You're white-haired enough to remember. Where did the 80 card width come from? Of course, from a card. Did they have images on card decks? Okay. Yeah. Or mag tape. Yeah. So they blocked these single card, hollow card images. I meant to bring one. Into 36 blocks, 36 card blocks. And then that chunk gets repeated. You either fill it with nulls, which is the old way that's illegal that'll blow AstroPi up. AstroPi squeals like crazy when you do that to it. Or you put in blanks. And I've seen some of the new spectroscopy software, well, from last year, 18 months ago, come in with nulls in those areas if this verifies the blank. You've got tables. You can have ASCII tables or binary tables. Remember that big Indian, little Indian thing? Okay. If you use fairly consistent tables, ones that got used a lot, they may be old, but they were around a lot, AstroPi will probably take care of you. If you don't, you're down to whittling your own, and you go through CFITS.io and do all that kind of stuff. This is a hyperlink. I'll match it so you guys can read it. Okay? For the FITS standard, there is a standard. It's up at your SART. I don't know how you can write a government standard so word flexible in the first word. There must be a lot of climate change going on. Next slide, please. You guys are familiar with Naxos. Like there's Naxos. You can have a Naxos 1, which is just one data, which is just a single spectrum where the values are the B units of stuff. They can be ADUs if you don't calibrate them, or they can be erg seconds, centimeters squared, or whatever, angstrom or hertz. If you have a three-dimensional data cube, you get that, and you get like image planes that are stacked up. NumPy, everybody understands all that stuff. You can have keywords, blah, blah, blah. Okay, next slide, please. Okay. You've got your critical keywords, simple, Naxos, blah, blah, B scale, and those kind of guys. They're always kind of have to be there. You've got somewhat standard layouts. You've got the single extension things, which can be anything, and you've got these little guys called MEFs, multi-extension formats. And that's where you can mash several things together. Think of it like zip without compression. And all the data is correlated in there. If I take my photometry image and I've done magic on it to get my single image, I run Sextractor on it, I can put the Sextractor table as a MEF table. And that way, my table follows my image. In your case, you might want to put a MEF table under there and only send the MEF tables file. That way, if you need the file, you can go back and tickle it and say, man, this looks bad. Show me what you got. Oh, look, birds in my That's cool. All right. Software, FITS.io and CFITS.io is the old way. AstroPi has improved it. Thank you very much. They're very rigid. You also have CCFITS, which is sort of a C++. Yes, you can do objects in C. C++ orientation to FITS.io, okay, with AstroPi at the bottom. Next slide, please. Kind of what it looks like. Keep going. You can go in if you trim. Remember, I've been advocating trimming instead of binning. You can go in and write this thing here, which is a logical to whatever, usually a physical to logical translation, that if you're in DS9 and you're on the pixel that's way down in the bottom corner, which by definition is 1, 1, okay? Although the picture guys, the computer scientists, I never understood why we did this. We put the 1, 1 up in the wrong corner. I mean, I guess we failed algebra enough. Yeah, there we go. Yeah. Okay, so, but what that would do then is it would say 1, 1 on the logical, but it might give you 100 by 300 because that was your clip boundary for that pixel, so that you do retain the information of where that thing came. So that's kind of important if you're in the trim game, and it blows different software up. That's a problem that I've been running into. Okay, so next slide. Okay, then we talked about the coordinates and the B unit. The B unit is one that's usually missing. By definition, it's an ADU, but otherwise it should be in something realistic. And in this case, it would be erg, second squared, centimeters. It can be in Janskys, watts per steradian per phase of the moon. I don't know. Next slide. Again, I had out 3 times. Thank you, Windows. Here's SARC. It's a place to go get some of this stuff. A program I highly encourage everybody to download. It's relatively platform agnostic. It'll run on a Pi, it'll run about anywhere. Is FITS Verify. There still is. Yeah, you can get the source or whatever you want. And what it'll do is it'll tell you what you did wrong, and you can go in and fix it. Epoch, I think, is that the one they don't like these days? Equinox. Equinox is a keyword they want us not to use anything. Okay. These are all interoperable. Jessica Mink at SAO has done some pretty fantastic things. She's got ways of dealing with oddball images that are actually worthwhile to. I wouldn't bother making a note. I wouldn't go there unless you have to. But and if you do, man, you're grateful for the work she did. And you can roll your own. And that brings me to a topic called Python. So next slide. You get libraries from various places. You can roll your own or not. SOFA is an IAU, Standards of Fundamental Astronomy. It's got people like Pat Wallace from Her Majesty's Nautical Almanac Office, Ken Seidelman from USNO, handfuls of routines. The USNO group is usually this Novas or Novas C. There's this gimmick, Sea Spice from JPL. If you really want to stay up for a long time, there are more bunnies down that hole than you can imagine. You can build your instrument, tell it where it points, and it tries to be accurate to within 1 meter and 1 nanosecond, anywhere in the solar system. Actually, guys should probably not play with that because you don't need to. Who cares about those kind of accuracies? But not, actually, Bob, you asked me a question many moons ago about where Kepler was. And I wrote Bill Postle over at LASP. I said, I don't see Kepler in the file or in the list. And about 3 o'clock in the afternoon, I get this thing back and said, try now. And he had gone all the way loop to JPL, and there it was, and it showed that because it was Earth following, and if using Earth coordinates, you would get one view of Jupiter, the Trojans, and a different, where it was, gave a different view. I don't think it really mattered much. And besides, Kepler died before you could use it, but now, you can roll your own. The roll it own choice, I think, right now is Python. Python is an environment. It's more about an opinion that has scripting capability in it. It was started by Guido van Hoosen because he hated Perl. How many people love Perl? I didn't think so. Okay. Pretty cryptic stuff. But the thing is, it has since it's an environment, we have to agree how we're going to interchange our information. And to do that, they had a thing called an egg that you could Python set up PY, and it would inflict it upon your system. Then they went to a wheel and environment type thing, where it'll carve out a chunk of your disk, and all the junk that it wants is in that ball. So it doesn't interfere with what your system is. Or you can run it in a Docker container. Probably your safest way to do it. And within that kind of an environment, you can come into AstroPy. Now, there are other things, but we'll show that in a minute. You get the core packages, the affiliated, the coordinated, and the infrastructures. The further down the list you go, the less widely accepted it is. But critical guys have done it for their instrument, and it may be generally applicable, so they make it available to you. So next slide. Okay. Keep going. Get over this pretty quick. This is what we aren't going to do because nobody sent me too many images, but keep going. Okay. Recognize this, Jim? Okay. Okay. This is a dump of, remember old memory dumps? You guys are old core dumps and stuff, yeah? Okay, yeah, there we go, dumps, grimacing. These are 4 bytes, okay? Byte 1, 2, 3, 4. These are 16-bit words, okay? 2 nibbles, in big Indian format, okay? Look up here, everything ends in 0. So they shifted it over by 4, which is a divide by 16. Well, this is because this is a 0 exposure, okay? There just wasn't much photons to be counted up there. There may be the occasional 1. I never found it. Well, you got 256 that you're scaling by some number. There's no gain information usually in the header, which is why I brought up the header to begin with. The chip off the 42 has got up to 8 gain amplifiers that you can have. I don't know what we're going to do with the 6. You guys talked about big images, right? Make the vector in there, it's going to flop them up quite a bit. So at the end of the day, though, be aware that this is the stuff that you convert to floating point numbers to try to put decimal points on. So that's something, if we co-add a bunch of them, we can get away with it. Okay, next slide. Okay, I think that's probably about it. Keep going. Science, keep going. One idea that I've been playing with, and this is going to be part of the discussion coming up, maybe not tonight, but in the future. Let me say this too, really quickly, since now I know most of you are definitely here, and anybody who didn't care left. What we plan to do with this workshop is to continue it with some Zoom sessions into the future. We'll probably set up like a Red Dwarf page thingy at aatel.info and fan that out to you guys. We have your email addresses. And that way we can get together, give you some homework, or you guys can generate some interesting homework for us all to do. We can get back around the campfire, see what's going on, make a few determinations, and start this process of developing for ourselves what our community really means by a lot of this stuff. Okay? One of the ones I've got is called flux radius for observation. And that goes to what John's been talking about. Just if I got a small aperture, I can only get so much flux. Bracket that with some signal to noise requirement, that actually defines a radius in the local space that I can see things. I can see O stars in other galaxies if I've got a big telescope. I can't see them locally if they're halfway across the galaxy, but I can see them locally, like in the Orion's Belt and stuff. So there is a radius around some of things like that. But that gets into a bunch of discussions about flux calibrating is one of the basics of that. And then we get into a couple of things here that go back into, that should be filter transformation as well as filter transmission. Each filter, if I buy 2 filters from a vendor, chances are they're going to be slightly different. And so Eric Ghost and I have been talking about different ways that we can qualify these guys, so that we can go about doing our own filter transformations. But everything in your system, you've got to qualify and transform. Good times to do it, moonlit nights, bad seeing. Those are some pretty good nights to work with some of these. Next slide. Goes back to the big questions that we keep dancing around. If we're going to publish, what's the level that we needed? Did we achieve it? What are our error bars? And I think if we can improve that aspect of a lot of the work that we do, and I'm guilty of it too, so I'm not calling anybody out on this. The old saw about signal to noise, if I want a 100% or a 1% rather observation, I need 10,000 photons. The square root, that's going to be 100. There's a bunch of stuff. I'm sure John has got some good techniques that we can borrow from him to kind of cover that. Yeah. What do we do if we put noise in the system, like this random radio telegraph noise? That means that 10,000 may turn into 15,000. It's not going to turn into 1 million, but we may want to bump that number up to pad the headroom so that when we whittle it back down, it comes back as 1% photometry. And again, remember the earlier part I said, the QE on these chips are up. It may very well be that if we increase that number, we keep the same exposure time, more or less, maybe a few seconds different. For the really, really dim things with a small aperture, you'll be on it forever. Like, what is it? 1,800 seconds for some of those spectrograph observations. Okay, next slide. Filters are a big deal. Here's a question for Arnie. Where do we sit and get in filters these days? Bob? I don't want to hear that thing, do I? They'll be bald as the rest of us from this. No, I can't get filters.
There actually are 2 sources as of right now that do Johnson Cousins filters. Do a pretty good job on them as far as I can tell. Chroma has a new set that's out, not the square top ones. And Botter is also producing filters.
Have they shipped?
Chroma I have a set of, Botter I do not have a set of, but then I haven't asked for a set either. Okay. I should.
Well, Dose is waiting for some from Astrodon and from Botter, I guess. Botter said through OPT, they said that they were any minute now. And Jim, didn't you just get a set from like Custom Scientific? Okay, good time to ask them. Okay, we'll take that one offline then.
Yeah. Yeah, I will reserve judgment on the square top filters until after I run my super duper program to do them. I have tested the Chroma filters and they're okay. They're not as good as Astrodon, but Astrodon isn't around anymore. And like I said, I haven't seen the Botter filters yet. And I am perfectly willing to test any set of filters from any vendor. All they have to do is send them to me. Okay. And the Sloans are fine because they are all square top, well defined, and they seem to come from all vendors, and they all seem to do a good job.
But there are the Pan-Star filters, as we talked a little bit earlier about Conway and Company's RepCat 2. And those are curvy ones.
That I don't know about. Panstar uses Sloan filters. The only difference is out at the red M, Z short, and Y.
Next
which
slide.
aren't.
Okay. This is your friend and your enemy. Okay, can you click on that and make a web page appear, do you think? Oh, it'll scare the heck out of the home audience. I keep pushing on it and I know we're in a conference room.
Another SONNAP rather than the Spanish Virtual Observatory is the Asiago.
Yes. Well, there's also has like every filter description from everywhere, because I go up there all the time for the Apache Point filters, got Panstar filters up there. And they've also got Astrodon. Some of the, okay, that's the good news. The bad news is some of the filter curves have the observatory's sensor curve built into them, so you got to be careful about that. There we go. So click on Pansars. The light's already on Pansars. Scroll down a little bit. And there's kind of what some of their filters look like. And those are a little curvy. Now, if you click on one, pick on G. That's a good one. Somewhere like this guy right here. God, this thing is working great today. They actually give you the transmission curve that you can download as an ASCII table. Now, it may not work for you, but it's enough to learn with, or to just do some back of the envelope, can I get away with it type stuff.
Okay, is that the transmission curve for the filter, or is that a transmission curve for the system?
I think it's system in Pansars.
So those are two different things.
No, but it's a good thing, because that means that this reflects Conray's original data. And I don't know what he did to his data. I don't know whether he brought it back to a standard G or whether he left it in Pansars for that. I don't use it enough anymore to know. One thing I ask Pansars for is what is the variance of that star? And if it's not wiggly, then I can trust it to be a reasonable field star to use for other reasons. Because it's not very big, or it's not too big. That's what I say around you. Okay, let's go back and wrap it up here.
I just noticed, I want to came in on the chat. Eric noticed that I just received this Sloan G prime 50 millimeter round filter provider. Will test against Astrodon lone filter this fall.
Thank you, Eric. And for Eric. We waited months for that filter. Okay. All right. Yeah. There are different magnitude standards. I'm just going to mention really quickly in passing, Johnson and AB. Just be careful what catalog you use and what does that really mean in terms of flux. That's really all that translates into. Oh, and one other thing I will mention is you have a hydrogen alpha filter and you're doing observations, particularly of galaxies. Somebody yells at you, quick, calculate the Hubble constant. And we found out that it was in the S2 filter. And we did our hydrogen alpha observations at night using the S2 filter. Hand wavy is all get out. Okay? All right, next slide. Oh, okay. There's gain, there's E-gain, there's a whole bunch of confusion in there. I like to stick to that particular word, but we've got to come up with some meaning outside of that. And it basically just means for that chunk of the sensor under that amplifier's control, what do I need to do to turn the ADUs back into a self-consistent fashion, and essentially into photon clouds? Okay? Next slide. Keep going. Keep going. I think that's pretty much it. Oh, wait, I promised you something before. This is yeah. There's a thing called red noise that I kind of got interested in, which basically says there's a whole bunch of different things that are going on that can put noise back in your system. And it's not necessarily that it's a 1 over F2, F squared type of noise source. So when you're putting your error bars together, just remember there's a bunch of different statistics you got to use. Next slide. Okay, that's it. All right. That's pretty good. There's one or two that you're missing that I didn't. I put the wrong one on the thumb drive. Sorry. Okay. Now for the fun part. Questions? Alan.
back, you had something called a pivot frequency.
Pivot frequency?
Well, it said pivot.
Pivot? No, it should be pivot.
That we just passed.
The Spiel checker got me.
So what is that?
Pivot frequency means half the energy is to one side of that particular wavelength, half the energy of the filter is in the other half.
Scale.
Yes,
It's fluctuated center or energy?
energy. It's nu related.
Oh, because the different colors have different energy.
Yeah.
So
What's new?
the bluer end of the frequency, the bluer end of the bandpass, you weight more heavily.
Yeah.
It's
The SVO tables go into mind-numbing detail about all of that. And there are other ways, there are other fiddly frequency thingies that you can use. And again, it kind of goes back to what you're doing. And a lot of it goes back to the black body. How many people here love the black body? Okay. It's going to be a long, okay, next year's workshop. What means black body? Okay. It goes down into local thermodynamic equilibrium versus non-local thermodynamic equilibrium, and flare stars. If you have a flare, this thing's at a different black body than that thing, and these things look taller than those things. That's pretty much it in a nutshell. Okay. Next question. I'm getting tired. My hip's hurting.
We'll take questions, but also be aware there's alcohol across the hallway.
I'm up for a beer.
Okay. Trev, they'll make more sense over there.
I'm around, you know, until the cows come home. I'm leaving Sunday morning. Actually, my wife's coming in Saturday night, so, but she'll stay in the room because she doesn't have any COVID. And I'll probably already have it, so she'll live long enough to get me home, and then we'll see what happens. And my estate will be auctioning my equipment. Okay, which one? Yeah, okay. Give me my beer back.
If you're auctioning your equipment, I don't want that crappy QHY 600 you were talking about.
No. The reason that it's bad is I ran a piece of equipment and damaged the anti-reflection coating. Within a week, they had one delivered to me. Okay, yeah. The one that when you put it in DS9 and you log stretch the 0, it looks like a hypernova went off, and you find out the counts are 7 different. Yeah, okay. We'll talk a little bit about that. I'll introduce you guys to the Make Stats. What is that? What do I call that thing? It's hard. Make 2D Stats Cube. It's learning new tricks. Good. Thank you all. I really appreciate it. I'm sorry.
Thank you, Wayne.
I gave you 15 minutes and 3 hours.
Well done.